I'm very excited to have our speaker. He's been on our wish list of being a speaker for some time now. He has quite a storied career going back to the very early days of CMOS sensor design. We were just talking earlier in Micron when they used to make memory chips, which is where CMOS imagers were born. He's since then worked for a set of imaging companies. I don't know if I can mention all of them, but certainly goes through the history of what CMOS imaging is all about. But tonight is not about CMOS imaging. So what Fred's going to talk about tonight is the next step after capturing photons. So I'd like to introduce our speaker, Fred Brady, and thank you so much for being here.
Right. Yep. Thank you. Nice to meet everyone. Fred Brady, and I'll be talking about intelligent sensors for AI products. So we're still capturing photons, but what we want to do is optimize the processing for AI rather than make pretty pictures for everybody to go ooh and ah over. So I'll give a short introduction to Oculi, where I'm the Chief Technical Product Officer. Talk a little bit about smart sensing in general, the challenges with smart sensing, our approach, and a brief look at the future. The Oculi is based on, the technology is based on Johns Hopkins IP, developed by Charles Rizix, who is the CEO and co-founder of Oculi. And the original technology developed at Hopkins for low latency and power efficient vision systems, focusing on defense applications. And it was spun out in 2019, focused on commercial sector. And for defense applications, focused on things like drones, having self-guided drones, or high-speed imaging, like tracking missiles and guns and so on like that. And you see how fast it can be. So moving to smart sensor, generally the smart sensor market is a very large market, billions and billions, and looking to grow, worldwide, all the different segments looking to grow, become, good growth rate over years. And what's driving this growth rate, number of items, energy efficiency, a lot of it's legislation, but green driving legislation to make things more energy efficient. A lot of interest in smart devices to not just count people, but to really understand what people are doing. Are they paying attention? Or are they happy? Are they looking at something else? Increasing productivity, through more automation, communication, more robotics, more smart things, more smart appliances. And then finally, better data, more data for better decision making, getting the whole picture, like building maintenance, keeping the building operating optimally. These are some of the key drivers. And you bring it down a little bit, let's look at home sensor application. Some areas are like smart appliances, TVs. That can be know what people are doing, if they're paying attention or not, or AC heating units that kind of optimize if somebody's in a room or not. Enhanced security, looking out what's going outside, notifying homeowners if there's anything suspicious. You can optimize heating and cooling, still looking at, the not heating areas where there's nobody, and, making sure where people are is adequately heated or cooled. And then, of course, smart lighting control, not having lights on where they're not needed, and so on. And if you look at like office and buildings, there's some similar themes there. Occupancy flow tracking, knowing where people are, where they're moving, where they're congregating, where they're not, and you don't have to take care of that area. Security, keeping everything safe and monitoring what's going on. Energy costs, again, optimizing the heating and cooling for where people are, and minimizing it where they're not congregating or meeting. Environmental monitoring, just general environment, keeping it comfortable and looking for issues. And then similar themes for smart cities, monitoring traffic and parking, where are the parking spots available, what's the traffic flow, where is traffic piling up, security, kind of keeping track of what's going on, and environmental monitoring, just snow, water, floods, and so on. And then finally, smart lighting, having lighting matching what's needed for the current environment, whether it's darker than usual due to clouds or whatnot. So those are all kind of areas people are looking at. That's all pretty interesting, but of course, there's costs associated with that. A lot of energy, operating a lot of more sensors. It takes a lot of energy. Moving lots of data volumes around from the edge to the server to the cloud, that takes a lot of energy. Storing large volumes of data, that's expensive. And of course, there's latency, moving data from the edge to the cloud, reacting, back to the cloud, to the edge, long latency there. And then another cost is privacy. More data equals less privacy. And specifically with image sensors, more data can equal no privacy. And there's a lot of trends there in terms of legislation, especially in Europe, trying to protect privacy. And here's one example here where people had a ring and kind of monitoring their daughters, making sure they're safe, and somebody hacked into it and harassed their daughter. So we kind of, we want to be able to protect against that kind of stuff. So that's all the costs. So how do we kind of address these challenges? Look generically at the Internet of Things. There's a number of layers. There's the sensors at the forefront. Typically, they're pretty simple. Then we have the edge layer, which is we're collecting the data, storing a little bit of it. Then you have the fog layer of the server, doing some data analysis, some response. And you have the cloud layer, which takes care of the big data and data warehousing. And there's a lot of flow back and forth here. So to make things better and faster and lower power, if we do things more cloud-based, then the processing and response time is slower. If you do things more on the edge, then the processing and response time is faster. So that's the general thing we want to do, is move decision-making toward the sensor and keep personal data on the sensor. So that's kind of generic, so specifically for cameras and imaging, how to move this decision-making and privacy to the edge and move it off the cloud as much as possible. So one challenge is today, the sensors are not efficient for vision AI and for sensing. They're developed for human perception. So if you want to know, we want to monitor, make sure all the kids that are on the bus are on the bus. We have some megapixel camera that sends the data to this power-hungry AI processor just to get some metadata out that, the number of kids on the bus is correct. So today's solutions are slow, power-hungry, and expensive just for getting the metadata. But we can think differently. So the legacy sensors focus on getting the image out and making pretty images, which is needed for certain applications. But if what we want to do is focus on outputting just the relevant information that the AI or machine needs, and just output that basic amount of information like person is present. That's kind of what we're focused on. This Oculi is moving from full image processing to pixel processing. So to reiterate, our solution is just the data needed for AI. So we're trying to push as much intelligence to the pixel as we can, and to solve like the power, cost, and privacy concerns. So at the pixel, we put the analog, not just the photodiode, but the ADD converter, processing, and memory. So it's all on chip. So with that, we can just put out the metadata, 11 kids on the bus, and reduce all that time to move the pixel data around, do a lot of analysis, and so on. So just comparing, a standard sensor with a microcontroller to Oculi approach. Look at a standard sensor. There's a very simple pixel array, and it outputs to the periphery, the full image, and you pass all that through the ADC, and then you have some digital calculations, demosaic and whatnot, move all the information again, then you have to make it nice and pretty. So there's the IQ pipeline, make it look pretty and do all the corrections and so on. And then you output that to the microcontroller for AI analysis. And that tells the system processor, okay, I found 4 faces. And it just, all that just defined 4 faces. By pushing things to the edge, we can do all that in parallel in the pixel. So we have all the conversion and the algorithms and filters on the pixel. And then we just output sparse output. In this case, we just output just the faces. And then the AI engine, which is also in the periphery, just needs to look at this limited amount of data to say, yeah, there's 4 faces or 3 faces, and just tells the system processor 4 faces. So by pushing intelligence to the edge, we can make decisions quickly and early as to what is useful data. And for our sensor, we have a lot of different output modes. We have smart events, which is just outputting pixels that meet a selectable criteria. And it can be based on intensity or rate of change, and that's really used for human object detection and so on. We can output basic signals like number of people or swipe direction, just outputting that, and then that's complete privacy there. Sometimes you do want to put, have inferencing on a microcontroller. So there's applications we can output through all pixel and standard formats. And we can also output arbitrary order for event sensing type applications, so low latency, asynchronous. And finally, like I just showed, we can output, without bending, we can output regions of interest. So just focusing on what's of interest, like the face or an eye, and then reduce power and latency by just working on that one key area of the scene. Here's some output examples with, this is the scene in the upper left. On the upper right, here's an example of a sparse signal output where the 2 people converted into a certain kind of signals. We can output just ROI, you can see the 2 people here, or the metadata, which is, the person, there's 2 people and they're located here. And so depending what's needed, we have that flexibility, and, of course it's lower power for here, and, this is low power, but all at decreasing power. And for presence detection, with this kind of just keeping low power and just outputting the metadata, for 1 year, you can run the camera on the AA battery. So very, very low power, operating in the metadata mode. And you talk about presence detection. Currently, the market is PIR, and there's some radar coming on. So we kind of compared our solution to PIR and radar. So here's PIR, and you see here's the scene. On the right is the sparse signal for Oculi. On the bottom right is Oculi edited output. And then the bottom left here is the PIR detector output. And you can see the PIR thinks the dog is a person. And I'll run the video here. You can see with Oculi, we get data. And we able to see it's not a person, it's a dog. But when a person walks in the scene, then with the metadata form, we can say, oh yeah, there's a person there, and then we output that there, we detected a person based on this actual data. And looking at, again, comparing versus radar, start off here, it looks like radar is detected 2 people, but actually it did some tracking, and it's really only has 1 person in there. And Oculi has 2, and you'll see as the lady gets up and walks away, the other image goes away. Well, we're always able to have the right number of people in there. And then, it lost that there's, a person there. So the 2 techniques that are most out there, PIR and radar, both have a lot of accuracy issues. And if we look at comparing the energy latent savings, focusing on presence detection versus edge processing or cloud processing versus the Intellipixel, you see for energy, basically we can get, say, 70-ish X improvement for versus edge processing and over 100X for cloud. And then for latency, we can get like 20, 30-ish, and for cloud, 3 orders of magnitude. And then the privacy, since we keep everything on the PICs on the chip, there's no privacy risk here. The edge processing a little bit hackable, and cloud processing, of course, is no privacy. And here's some other examples. We did a hackathon at the TinyML 2023, and looking at people crossing the road. The conventional VGA solution had a lot of issues, was seeing complexity, and wasn't as accurate, like 60% versus 81. This from the Oculi SPU, and it had a lot longer inference time. So a lot improved, highly improved accuracy and inference time for the Oculi approach. In looking at people detection based on the actionable signals, you can see that there's this keeping the accuracy the same, we can do like 25x reduction in the inference time. So much faster than running neural network on the full frame without the accuracy a little bit higher for the neural network, but 95% is good enough. And always on presence detection is a growing area. You have the sensors on all the time. And so power, of course, is important in those. And we looked at some commercially available solutions. And latency, we looked at 2 different options for our SPU. One is just doing all the processing on the SPU, and the other one is waking up a microcontroller occasionally to do heavier duty inferencing. And you can say in both those cases, there's a significant savings in power and significant reduction in latency. And covering face detection again with imaging versus vision. With the conventional, you have good accuracy, but the inference time is very long. Or here's accuracy. Inference time is very long. Just looking at ROIs and having less data, we can get good accuracy and 10x faster inferencing. In this case, with cutting the ROIs back a little bit more, we can still maintain not too bad accuracy and really cut the energy down and inference time down. And again, looking at always on, but for face detection versus presence detection, we did a couple of comparisons. And in this case, we can use the Oculi with the microcontroller. We wake up and still be able to do much better latency, and then huge improvement in power related to the minimizing the data. Besides the presence detection and face detection, another area for us of interest is pupil detection, and that can be done with high accuracy and very fast. With a conventional camera, we found it was like about 89–90% accurate, and took a long time for inference. Again, focusing, just reducing the area that needed to look at, and get almost as good accuracy and inference time like 10x faster. And then the final example I have here is hand tracking. And this is looking at hand poses and trying to detect a hand from that. You can see when this kind of complex scene like this, the standard technique had some troubles and only detected one of the hands, or with this complicated scene, had trouble seeing all the fingers and knowing this was a hand. But by focusing on the ROI, we had able to get better accuracy for both and even seeing the smaller features. So focusing on the important pixels, significantly improved the accuracy. So just to wrap that up, main points is pushing intelligence to the pixel can really enables the pixel array to only output the needed data. And then this enables simultaneous improvements of faster sensing and lower power sensing. So not a trade-off, better at both, which is what AI applications need, without losing accuracy. And a glimpse ahead, one of the trends that's kind of increasing is sensor fusion, putting together different kinds of information, sensing and image and depth or audio and temperature. And so that's requiring more data, more and more energy. So with that trend, that further, I think it makes it more important, increasing its importance of putting intelligence at the edge, to keep the data and energy costs low. And here's an example from Sharp, AI Smart Link, which combines audio data with the built-in microphone and a camera, using all that together. So yeah, that's kind of my
Wonderful.
presentation.
Can you talk a little bit about the architecture? So it sounds like there's a CFA array, and then image data goes straight to an inference engine, so you don't have to go through all the image processing steps we normally would. Is that a true statement?
Right. I'd say, yeah. So if it's not for somebody to look at, a picture of the kids or something like that, yes, you can skip all that, make your die size smaller, which helps with costs, have things go faster, use less energy. So, so all that's helped by not having the image quality pipeline.
In the inference engine, are there, you mentioned a number of functions, right? If somebody said, wow, this is a great technology, and I want to build it to do I don't know, find clams on the ocean floor, right? Your inference engine probably isn't programmed for that. What is the development steps to go from what you have to something that a client would have, which would be a niche thing, which may not be what you currently have?
Yeah, I think inference engines are pretty flexible. It's more in the training.
Exactly.
Yeah, so I think there's not as long as you can have sufficient resolution to see the features you need to see, the inference engine, you can,
So the customer would give you a training set, or would you give them the tools to say, here's a sensor inference engine together, go forth and build your inference engine? How would that?
Yeah, I think that's a good question. So we have both models where we'll output. If I show the slide where we have different different output modes, so we can output what the partner company is looking for. So there's flexibility there, and we'll have some things we'll do ourselves, but right now we're a small company,
Okay.
So in the near term, for something like that, we would provide the data and then look for the partner company or customer to kind of do the training and so on.
So the product you have right now is an image sensor. Tell me what you have right now. Is it an image sensor with an inference engine on the same die? Then or do you have an option where, depending on what you want to get, you can get this resolution sensor, you can get this much inference engine size. I don't know what the right term is for that. Or is there a unit you already have, and then whatever fits on that is the way you go?
So we have two different things we're working on currently. One is we have a prototype called S11, and so that has some capability on it. And then we're designing our first sample chip. So that's like a internal test. And then additionally, we're using a lot of this data on the Raspberry Pi. So we have a Raspberry Pi simulator that simulates the output and shows people what the data is going to look like. And so on. So those are the three things we have at this point.
Very cool.
On your SPU on the package we're looking at right there, is that just one piece of silicon or is that more than one piece of silicon?
How are you, just to be clear, what's your definition of piece of silicon?
Well, okay. In terms of silicon, is it stacked?
Yes.
So
but I would consider, I thought before you were going, but yes, stacked is one piece of silicon. You do if you do wafer bonding.
Yeah, so it's wafer. How many silicon layers are in there?
Two.
Two, and is there a system and package in there also?
No.
Okay, so when you were showing one of your slides, you have the imager, the A to D memory, and your processing unit. I don't know which slide that was.
Right, I think this one you're.
Well, actually, this one's good enough. First off, you do an A to D per pixel, or is it A to D?
Yeah, per pixel. Yeah.
You're doing per pixel.
Right.
Okay, so then you do all that, and then so basically you have a process on your SPU. You actually are doing processing in the package. It's not separate from it. So
right,
you're calling that. I forget. You had the edge, you have the cloud, and then you were calling the package. What were you calling that?
So that's the sensor. If we go back to that. And trying to, I don't see, oh, here we go. Here's my pointer. Okay, yeah. So if we go down to here, sensor. So that's the package. So we're trying to move processing, it's like the edge. So we're trying to put things on the edge of the edge in the sensor, put as much in the sensor as possible.
Okay, so the edge is effectively going into the package.
Yes.
So this is getting similar to the Sony IMX, I think it's 500.
Yeah, so the difference, there's some differences there. The Sony IMX500 is like 12 megapixel. It's got, it's got to put out a pretty 12 megapixel picture, right? So it has all the overhead of making a pretty picture. It's got 12 megapixels, so it's a big die. So it's a very expensive beast because it's trying to do both sensing and making a pretty picture. So trying to cover both areas. So, we're trying to keep costs down, and you don't need 12 megapixels for sensing. All the AI people, nobody in AI wants that much, right? So we're trying to give people just the pixels they want.
Okay. All right. So the product that you had out where you were showing the faces, you were showing just detected faces of
right.
different people. Is that actually been built, or were you simulating that?
That one, that's a simulation. So
okay,
we're designing our first sample chip now.
Okay.
Yeah.
Okay. I was at a talk a few months ago with ST Micro, and they make a lot of mini boards about this big with a sensor in it with about 60 pixels by 60 pixels.
Right.
And they're basically, so if you walk up to like an ATM or a screen anywhere on the planet, it recognizes that a person's there and it turns on. And they have it coded up so, it looks, if you're looking at it, they want to know if you're looking at it or if you're looking to the left or the right. That's what they have. In that talk, the individual said that were able to fit their AI with only 2,900 fitting parameters. It's the first time I'd been at a talk where someone was talking about how few fitting parameters they used for their AI fit. Like they were just going up there. And then the question I have now is how many fitting parameters do you have available and what can you do with a limited number of fitting parameters?
Good question. I had to think about that one. So we're looking at both, say, neural network and then just classical, machine learning approaches, both see what's better and which is lighter, what we can do. So we're trying to do as much as we can with maybe, say, conventional machine learning without using a lot of neural network. But something like the TI, not the TI, the ST chip, still that was 60 pixels, that was probably a top sensor.
I can't remember.
I've seen something in that resolution range from them that's time of flight, but you're kind of limited. You can do a few things with 60 by 60, but there's a lot of things you can't do with a 60 by 60.
Yeah,
So
well, I was surprised they were able to do it. That kind of threw me for a loop there. Okay, but
well, there's some market where people are intentionally keeping the resolution below like 100 by 100 and claiming you have privacy because the resolution is so bad. You're not doing anything special, just like the resolution is bad, so low, so it's privacy by that. So I think that's partly part of it. And then time of flight is also very high power, so that's also another thing that's driving keeping it, the array size small for time of flight.
are you doing any time of flight?
Our solution is compatible with time of flight, being stacked so that you can put IR, SWIR, regular pixel, or time of flight. So that's all been done in the past. We're currently focusing on the commercial applications, visible commercial applications.
Kira, are you running at Global Foundries, or can you talk about this?
No.
Okay, yeah, that's fine. I have a pretty good idea where you need to be if you're running A to D per pixel. So yeah, so that's pretty tight node.
Yeah, I'm sure you can. Yeah, I'm sure you can ask me lots of detailed questions.
Yeah. No, because this is really interesting stuff. But yeah, the world's changing very quickly.
Mhm.
Yeah, like, are you planning on trying to hook this up with any AI type chips, like a Xilinx, some kind of processor?
We're looking at both. For some applications, you can do everything on board, and then some applications are more complex. And then in that case, our approach is going to be to like only wake up the microcontroller when it needs to do the inferencing, like do as much as possible, and then try to minimize the microcontroller. But sometimes maybe every 10 seconds, or I don't know, something like that, you need to do something with the microcontroller, and then something complex. So we want to support both.
Yeah, I mean, it seems ideally what you'd like to be able to do, have a little bit higher res part, and just ship back the metadata, like what this is and where it's going. And then maybe once a second, send back a small ROI with a picture of what it is, just for, bookkeeping or tagging.
Yeah.
Yes, moving on.
Yeah.
Do you see this as being useful for autonomous driving type applications, autonomous vehicles?
Yeah, it's got automotive applications. Currently, automotive market with all the qual requirements, stuff like that, it's a tough market for a startup to kind of get into. So we're not focused on that. We are talking to some automotive people. If some of it's a little bit easier, there's like, you still have occupancy sensing, in automotives, you have driver monitoring. So those could be areas that we're, interested in where maybe you need a little bit less, a little bit easier to get into for a startup and something that's needs to be outside or something like that.
Have you ever talked to D3, which is
D3? Yeah, we've talked to D3. Yeah.
Okay.
Yeah.
I invited Scott to join us, but
Okay.
So does your sensor, do you have color channels? Do you need color channels for what you're doing?
It's compatible if, for a lot of applications, black and white is okay. If you need to detect color, if you need to make a decision based on color, then you want a color sensor. It's compatible with color sensor. If you need, for some reason, you need to detect blue, like I'm looking for blue people. Pick something that will offend something. Yeah, so I look for blue people, so then you can set it up that way. But then you need the color filter. If your application is independent, you don't care about color or wavelength, then the monochromatic's fine.
Is it modular enough that you have the ability to do black and white only, or swap out and have a different sensor that has color filters? How does that work?
I mean, it would be a different camera. Yeah. I mean, you gotta it's wafer to wafer bonding, so you kind of have,
It'd be a different product.
it'd be a different product, yeah.
Okay.
Yeah.
Isn't it just a matter of just painting another CFA on top, right? If the network's been trained to deal with color CFA data,
Right, yeah,
then
yeah.
it can just,
Yeah, from a firmware point of view, yeah, the firmware should be okay. Yeah, it's more you need a different part that's been through the right processing.
Do you have data sets available to your team? You collected data sets to use to program stuff?
Yeah, I mean, we have an applications team that has done a lot of this, a lot of the demos here.
Can you tell us a little bit about Oculi? You know, how many people you have now located here?
15 people. There's 5 of us in Rochester, a few on the West Coast, a few in Asia, and a few in Middle East. So kind of spread out, spread out a little bit. Our official headquarters is Rochester.
very good.
And our circuit design team is in Rochester.
When was it started? How
The
long?
Oculi started 2019, I believe, and then the Rochester part we joined April
Of this year?
of this year. Yeah.
Okay.
Pretty new company.
Pretty new company. Yeah. So I know if you heard of Luminate.
You're part of the.
Yeah. So the last cohort last year, Charbel and Oculi won that cohort, got the $1 million prize, and hired a few of us with the Luminate award. So
Very good. Any other questions? Thank you. Thank you so
Thank
much.
you.